Okay, let's get started. Good afternoon. So we are continuing with, it should be on this one. Yeah, both of them are on. This one is on, right? Okay. I'm all wired up. I have two mics today, so let's see. Very good. So I think the topic is sequential machines. We started on it last time. The last lecture you saw on sequential machine is what I would call a classical lecture on sequential machines. You can open up many textbooks and you will find that kind of description, some state machine diagram or some transition diagram in terms of, truth tables, next state function, etc. And that's all wonderful and we need it because it's the fundamentals, it's the basis on which everything is going to be built. Unfortunately, at design level, we can't work at that level. It's too low level. So today what I'm going to present you is a new view of how sequential design should be done. And this is not found in any textbooks. You will see some notes to that effect in the lecture notes which we have passed out, right? So it's chapter 3 and 4, etc. in there. Okay, so pay attention to this, sequential circuits as modules with interfaces. So complex hardware is always viewed as a bunch of modules with input-output wires. But beyond that, it only says these wires are somehow connected to each other. So it's very, very structural view, the view we were emphasizing when we talked about combinational circuits. Right? So in combinational circuits, we say, oh, this box represents something, the full adder, and this box represents something else. And if you connect them, you get addition, 32-bit addition out of it. Now, you can think of a very complex hardware digital system also that way, that we have lots of modules, right? And they are connected in some fashion. This wire is connected to here and there and so on. That's not the view we're going to take. Okay? So this is the first thing you have to understand. We are moving away somewhat from the structural view, though structural view will be embedded inside what I have to say. Okay, so so this view, even though it's technically correct that these are boxes connected with wires with each other, it's not helpful in the design process. It does not adequately support, for example, what is called IP reuse. What is IP? IP, this is a buzzword that is used in the hardware industry all the time. Every block is referred to as IP, intellectual property, because you may design that and sell it to somebody else. So we all rely, whenever we do designs, we rely on lots of IP blocks, which are either designed by you, but lots of them are imported, sometimes from other companies, sometimes from within the same company, from other groups and so on. So IP reuse is a very, very big deal, and any methodology you have for design must be able to, make use of IP, otherwise it doesn't work. Now, the problem is, you have already seen it. 32-bit adder is no different from 16-bit adder. Right? So you need parameterization of some sort. And when you will learn about sequential circuits, there is room for much more sophisticated parameterization than just saying, the bit width is instead of 16, it's 32. So the way to think about this is you have a module and you may want to instantiate in many different ways. You put in the effort once, you wrote this module, it's highly parameterized. And if I'm designing a low power circuit, I may do it this way. If I'm designing a very high performance circuit, I may instantiate it some different way. And there is no, what should I say, one is not better than the other. It depends on the application. Where is this block going to be used? Later on, not in this course, but you will discover that, for example, FFT is a very, very important IP block. But FFTs are designed completely differently depending upon what rate at which you want to compute FFT, whether you want to emphasize low power in it or not, etc. So it's very important that multiple instantiation of a module for different performance and application requirements. Now the other thing is, as we see more and more complex digital designs, each IP block is so complex that there are companies which does design that block. you're going to use it. And if you can't use it in a black box manner, if using that block requires you to understand how that block functions, we'll make zero progress in this. So for example, when you have your cell phone, somebody is selling you the GPS module, right, which talks to the satellites up there trying to figure out the position, etc. Now that's a very, it's a very sophisticated device, sophisticated block. And of course, in our hardware design, we should be able to use that GPS module without understanding, exactly how it's implemented internally. And you will find once you start thinking like that, then this wired connection model doesn't work. It's too raw, it's too bottom, because you may change it tomorrow. You say instead of 16 wires, I have 32 because I want faster speed or something. So I'm saying we have to move away from this. So IPs have to be designed so that they can be, connected to each other to build a larger system. That's the goal here. The other equally important goal is in complex digital design is that you have so many blocks. Your cell phone, your smartphone has at least 80 important IP blocks in it. And we should be able to change one of them because I have a better idea, right, for how to implement that block without having to understand the whole phone, right? I should be able to plug it in, right, without having to worry that my whole design will go wrong. In other words, the interface of this module has to embody enough information so that functional correctness in some sense is guaranteed when you replace the block, as long as you have proven locally that the functionality of this block is the same as the one you're replacing it with. So this is extremely important. This is called modular refinement. I don't change the whole design at the same time, I change it piecemeal. And I want some guarantee that when I change this part, my whole design wouldn't become incorrect, functionally incorrect. Okay, so let me talk about why IP reuse is so difficult. So I love to tell this story, this is a real story. I used to have a company, which designed chips. And one day I was horrified to discover that on the same chip, there were 26 FIFOs, first in, first out queues of 23 different designs. Really, right? FIFO is a very simple device. You put something in, something comes out. There are 26 of them, not a surprise. What is surprising is 23 different designs. So I was so, and I talked to engineers. I said, why is it like that? They said, oh, his FIFO doesn't do what I want it to do. I said, why? Is it not like a FIFO? No, it's a FIFO. It's just not right for me. So I was very intrigued by this. So I got on to the plane. I was flying to San Diego, and I downloaded a version from the free FIFO, something available on internet. So first thing that shocked me was that this document was 23 pages. This document is not about how the FIFO is implemented. This document is about how to use the FIFO. I'm saying, whoa, I never knew FIFOs are that complicated. So here I have copied some things for you from this FIFO design. So this is what the block diagram that is given there, which makes sense at some level, data in, data out, push request, N, whatever N means, right, full, empty. So I was told that N refers to, if you know Verilog, that, oh, it's a inverted signal, so low means high in this case, low means 1. So that's just a naming convention that is being used in Verilog, and clock input and reset input. Now I'm reading this description. Okay, so it says, an occur occurs if a push is attempted while the FIFO is full. An error occurs when a push is attempted when the FIFO is full. So yeah, reasonable, of course. It's already full. If you try to push something in, some error should occur in that case, though you don't know what that means. Does that mean that the fire will come out, of the FIFO, or does it mean that, who knows what will happen, right? But something will go wrong. It's warning you. It says, and there is a conflict in simultaneous push and pop when FIFO is full. A simultaneous push and pop cannot occur when the FIFO is empty, since there is no pop data to prefetch. However, push data is captured in FIFO. So when you read these phrases, each one of them will make sense to you. A sensible thing, right? Somebody designed their FIFO and is trying to document everything, how you should use it. Say, don't do this. Or if you do this, be careful, this will happen. And then it gets, in my opinion, worse and worse. So now it's saying, it's certainly telling you something about what's going on inside. If you do this, then the internal read pointer to the, I can't read that far, incremented on the next edge, etc. What internal pointer? I'm talking of a FIFO, right? I don't want to know what's inside it. So this is absolutely anti-black box thing. Okay, and what I haven't drawn for you is that in this document, which is 23 pages long, there are all kinds of clock diagrams, what input-output looks like, etc. And you cannot, this is not a document that you can reference, because such comments are spread all over the place. So if you want to find out how do I use this FIFO, you are expected to read all 23 pages, right? You say, well, it was documented, you just didn't read it. So you can't consult it properly, this document. So I think the problem with such descriptions is that it's mixing functionality and implementation. Functionality is we do NQ, DQ to this thing. We maybe want to test for full and empty, of this FIFO. Implementation is what's going on inside it, right? These two things should never be mixed, so when we give the functional description of it, we should not refer to what's happening inside it. And it defines the use of these methods or the use of these functions on the FIFO in a pretty ad hoc manner, because there is no systematic way to search it. So what I'm leading to is, if you want a proper view of this, we need a better way of defining interfaces to these modules. We cannot think of these interfaces in terms of wires going in and out, because if you think like that, it's too low level and you'll get wiped out. You'll be constantly worrying about things that you should not be worrying about. Okay, so what is an alternative? So before I go to FIFO, let me revisit what you saw last time, which was a modulo 4 counter. What do you do to a modulo 4 counter? So it's there, right? You can increment it. So there is a method which says whenever I execute that method, the counter should get incremented by 1. And there is another method called read. Anytime I can go and read it. So it tells me what is the value, current value in the modulo counter. Make sense? Right? I mean, that was the intent when we designed that modulo counter last time, when we designed the circuit for it. So what I would like to do is write down an interface definition of the kind that is shown here. That interface of a counter has two methods. One is an action method called increment, and that's all it says. So you can do, by action we mean it's going to change the state of the system. It's going to do some action inside, right? That's all you know. And it has no arguments in it. And the second thing is, it has a read, which is like a read function. It's an output function from it, and it returns 2 bits, and that's it. That's all you know. So these are the two things that must be defined for a modulo 4 counter, and you can generalize for modulo n counter. The parameter there will change from 2 bits to log n bits. So there are many things that are being implied here. One, whenever I write down a module, it has some internal state. You don't know what that state is, but there is some internal state that is being wrapped around in this. The second thing is, internal state can only be read and manipulated by the methods of the module. What are the methods of the module? There are only 2, right? Either you can increment it or you can read it, and when you read it, it doesn't affect the state of the module, because that's what is being declared by the type. It's not an action thing, it's just a read function, right? It's a value function, sometimes called. On the other hand, increment is an action method. That means it's going to change the state of the module. An action specifies which state elements are to be modified. This is internally something is happening, right? Outside you don't know what is being modified. All you know is something is being modified. And actions are atomic. So when I say increment, suppose there were many flip-flops inside it or many registers inside it. Whichever ones I want to modify, either all of them will simultaneously get modified or none of them will get modified. In this particular case, if you remember, we were using 2 flip-flops inside, 2 bits. And we were setting them both. So what that says is, whenever I do increment, atomically, the state of the system changes. And any in-between states are not visible. There is no program you can write using this kind of a module which will let you see what's happening inside, right? These are the only 2 observations that can be made about the system. Now, those of you who have seen some object-oriented language with types like Java or C++, this is exactly like a module, right? Like a class definition in those languages. And this is a very deep idea that you should really carry through, in programming as well as in hardware design, that when we say something has a type, something has an interface, what we are saying is this object can only be manipulated using these methods. And these methods are specified in the interface. Right? So sometimes we use the fancy word like it's an abstract data type. It's some data type, right, which can only be manipulated using increment and read operations. So this is the thing we will enforce very rigorously. There is no cheating involved anywhere. You will not be able to see anything inside a module. Okay, so let's see how we might write it in BlueSpec, this module. Okay, so now I'm talking of the implementation of this interface. So by convention, there is no, you can use whatever name you want, but we often use make counter, MK counter. And you have to specify the type of entity you are creating. What type of entity we are creating? A counter, right? Counter is that interface definition. So now we have an obligation. If we are creating a counter, it has 2 methods in it. So this implementation must provide these 2 methods. So there has to be a method called increment inside, and there is a method called read inside. You have to provide me the implementation of these methods. Make sense? Yes?
So we defined the counter interface,
yes,
right? And here we're defining a module. And what's the difference between a module and an interface?
Very good. So who's going to answer that question? Yes?
The interface exists as like a thing you're going to make an instance of, but you can actually use the interface like as a real thing.
Interface is a type. It's telling you some high-level properties. You can give many different implementations that implement the same interface. So now what we are giving is an implementation which will try to produce that interface, right? So now in this, all I'm saying is, if you claim it's implementing the counter, how do I know that? Because you have declared the type, make counter, right? So that's the type of object you're making. Then it must be the case that you have 2 definitions, method action inc and method read, right? Yep.
Our interface is kind of like interface in Java.
Yes.
And then the module is a class.
Right. Mm-hmm. So you have the class object, and interface is the class definition, right? Okay. So now the next thing we have to look at is, yes.
Have something like private functions?
Let's not go there yet, right? So let's just, I want to draw analogies with conventional programming, but only as much as is necessary, because we'll also differ from that. So I want to just keep moving into whatever we are doing here. Okay, so the next thing you'll have to decide is, whenever you are implementing something, is what are the state elements? What do we need to implement this module? And what you saw last time was that we had 2 registers, right? We had 2 flip-flops. I'm just calling it register counter, which is, how big is it? 2 bits, right? It's 2 bits wide. This is the state specification. And this thing here, mark this because there are going to be many, many different types of left arrows. So look at this left arrow. Whenever you see this, you are instantiating it. You're saying, please make me a register. Okay, what is this thing? The initial value. I want the initial value of this register to be 0. Okay, so what have you seen? We need a way of making registers, so that is on the right hand side in this. Instantiating it, and whatever I'm producing from it, I'm writing down the type of it. What is the type of it? It's a register. How wide? 2 bits wide, right? Can you read all that in the definition over here? Very good. Okay, so now I'm ready to implement the read method. What does read method do? It reads the counter, right? So you just return whatever the counter is, right? So those register values will be returned here. Yep.
Wait, sorry, what is mkread?
Make me a module. Make me a counter. This is foo. You could say foo, right? The way you know you are making a counter is because of the type definition that is written. The type of entity you are making here is this. Oh, sorry, this. So this name is irrelevant. You can use whatever name you want, but this is the thing that tells me that I'm making a counter. And counter, as you can see, is the definition here that I gave for the interface.
And then what is reg?
So similarly, this is suggestive of the fact that I'm making a register, right, whose initial value is 0. But the only way you know that it's a register is because you wrote down this. So anytime you want to instantiate something, you have to know the module that can make it. So somebody, I'm assuming somebody has told us how to make registers, right? And that program is embedded inside this module, make registers. It makes registers. Does that make sense? So it's a hierarchical thing. Registers is where it bottoms out, right? So the lowest level thing we'll deal with is make me a register.
So what is instantiate doing in this case?
So if I execute this twice, it'll give me 2 different registers. So I can say, for example, counter 1, make me a reg, right? Counter 2, make me a reg. So these are 2 different counters. So left arrow, whenever you use, you get a new thing. In object-oriented languages, it will be like saying a new object, right? Make me a fresh object. Instantiating it. Yep.
So registers are going to be things that I'm guessing we're going to use a lot.
Yes.
I'm wondering if the make reg function is
Yep.
something that's BlueSpec built in, or
Yes.
something that you guys give us.
It's well, we are same as BlueSpec in this case, but but it is really such a low-level primitive that will be implemented outside the language.
Okay,
So it's outside BlueSpec, right?
So this make reg function is not built in. It's something that is
Right, but I think there is a way to overshadow everything in BlueSpec. So you might be able to, if you have a different idea for a register, there will be a way of doing that also. But please don't change this name, because your code will become more and more unreadable more you change these things. So please don't use bizarre names when you're naming things, even though names are completely first-class things. I mean, there is nothing built in about names. Any other question? Yes?
So do we define the read method when we instantiate counter as opposed to when we're defining interface?
That's right. So interface doesn't tell me how increment works. It doesn't tell me what read reads, right? It just says these 2 methods must be present, right? So now I'm actually implementing the counter. So I'm saying, I have said, okay, this C and T thing is my counter, and when I want to read it, I just return the value in the register. Good? Okay.
So interface counter is sort of like the constructor, or
we can't go there, but the only thing I want you to remember is interface is always talking about some object. And interface methods are telling you what is available to you to manipulate that object. Right? So counter objects can be manipulated only in two ways, increment and read. And read doesn't do anything, I mean, it just returns something, right? You don't know what it returns, but it returns something, and increment affects the state of the system. That's why it's an action method. Got it?
yeah.
Very good. Okay, so now I'm trying to implement the increment method, because I have to actually, that's the main thing in this. I'm saying counter gets something, My attempt here is to write somehow that CNT plus 1, but we are doing very low level work, so we have to actually show the implementation. Does anybody remember what the definition of this increment was from last time? So what I'm writing here is an action, right? So any time you have to set the value of a register, right, it's an action. So this whole thing is an action. To understand the syntax of it, most important thing is this: a new kind of left arrow has appeared. So this is a double arrow which you will use a lot. And this always stands for assignment to a register. So you have something defined, which is a register here, and you're saying there is going to be some value computer on the right hand side, put it in there. Yes?
Is the benefit of declaring the interface separate from the module just that you can make different modules that have like the same...
Precisely, yes, yes. Yes, that's very important in this. So for the same interface definition, we may want to give many different implementations. For the same type definition, for the same interface, I may want to give many different implementations, right? In many languages, these things are synonymous. I define the interface and the implementation together. That's actually the preferred way in functional languages, right? But here it's separated. I mean, this has been the tradition in this world. And it has some advantages, though it does make things somewhat more verbose. Yes?
It's like the interface is only telling the compiler in which ways you can put that thing in a circuit. Is it something like this? Like the only information it has is where it has...
You can think about it more abstractly. Interface is the definition, high-level interface definition of an object, right? So you're saying there is some things I want to call counter. So the minimum requirement is, if you want to call something a counter, it must have these two methods, right? It must have an increment method, it must have a read method. Okay, and we can generalize from that. That doesn't mean that, I mean, we have to specify more, otherwise they will get different, Okay, so this is from last time, so if you saw, what was the value of Q, right, in that we had Q0 and Q1. So, one of the bits was just, we were taking the complement of it, right, when we wanted to increment it by 1. And the other bit we were taking exclusive OR. So this you can go and verify from the transition tables. Howsoever you come up with, I don't care. This is how you will write it in BlueSpec when it's time to actually code it in there. So let me just relate it to what the code is and what this notation implies, the notation we saw last time. This is the way to think about it. I have inserted these things here, t plus 1, t, t, t. Do you understand what that means? Right? Anything you see on the right hand side, you're looking at the present value of it. Time t, let's assume right now it's time t. And what is this? You are saying the next state of counter will be whatever I have defined on the right hand side. So it's only visible in the next cycle. Anything you do on the right hand side has no impact unless it's assigned to a counter. And whatever is assigned to a counter is not visible right now. It can only be visible in the next cycle. So that's why we never write t plus 1 kind of things here. Right hand side always referring to the current time. The left hand side always referring to the state of the next situation. You know, what will be the value of counter in the next cycle. Yep.
What's the reason we use like arrows instead of equals?
Say that again.
What's the reason we use arrows instead of equals?
Ah, very good question. So who's going to answer that? You answer it.
I am.
Yes. Why is it not an equal sign?
My guess is that we're working with registers, so you want different.
Right. You see, equal sign, whenever we use in this language, it really means equality. It always means that this thing is equal to this. Or we just use it for giving names to things. You know, this gigantic expression, I don't want to write it over and over again. I'm going to call it foo from now on. And then I use foo everywhere. Register is not like that. You are saying, so you could have, for example, written here, this value here, you could have written foo equals this value. And then you could have written count this funny symbol foo. Does that make sense?
Yeah.
So equality is only used for naming things, while left arrow is always about assignment. You know, what will be the next state? What will be the next state?
So why creating an instance of count use a type and then assigning the value?
There are different functions, right? So the first, you know, left arrow I showed you, that's saying instantiate, make me one. Right? While this is something dynamic, you are saying, because all the instantiation in this language are done at compile time. There is no dynamics to this. All the modules you're going to make will be made at compile time. So it's not like an object-oriented language in that sense, because there is no dynamism in object creation, right? It's all fixed. Good. So, right? And I'm not going to spend time on this, but you already saw this much circuit last time, and all I have to do is to package it in my funny thing. You know, I draw another box, and the input of this box is going to be called ink, and the output is going to be called read. And ink, whatever, you know, whenever you execute that, I just connected it to the here, right? It's connected to this enable wire for those things. Now, I'm going to give you a very systematic way of deriving hardware in the next lecture. Today, let's focus on programming. Let's focus on how to write down these modules, and let's work with slightly more complex examples, you know, so that you become familiar with the syntax of the language as well as the concept that is being captured in this. Okay, so this is what you get over here. Let's do another example, FIFO, right? That's where the story began. So if I gave you a definition like this, a FIFO module, does this definition make sense to you? By definition, I mean the interface. Is it self-evident what this is doing or saying? He's saying there are only these 5 questions you can ask. These 5 methods are available on this FIFO, like is it full, is it not full, is it not empty, okay, action, because we want to enqueue inside it. Does anybody remember what T is there? Yes?
Is T the type of the things we're going to
Fantastic.
inside the FIFO?
Right. You see, FIFO doesn't depend upon the type of things we store, right? But when we make it, we have to specify what type of values it's holding. So it's a parameterized thing. You can say type FIFO of anything, type T, right? And you have to give me a value of that type. But it does, in a very clever way, it's saying all the elements of the FIFO have to be of the same type. You can't keep changing the type because it's said it's type T, whatever it is. So this is so straightforward, this interface definition, I don't have to explain it. I hope everybody understands. I have also drawn this picture on the right hand side here, that whenever I want to do NQ, I'll be enabling it, right? And I'll be giving some piece of data. Whenever I want to DQ it, I just say poke it, say DQ, right? So it'll do something inside. And does everybody see that both of these have to be action methods? They're affecting the state that is inside the FIFO, right? Anytime you do NQ and DQ. And first is simply a read thing. It reads the latest value in it. So this is the type variable over here. They all have to be consistent. If you wrote T, T1, T2, that'll be a very strange FIFO. Right, so all of them have to be the same T. Yes?
So can we construct a method which has a return value and does an action, or do we have to decouple them?
You don't have to decouple them. So it'll come up very soon. Yeah. Yep.
So where did EN happen in the method?
It doesn't. So that's the thing. That's why, this is the picture on the right. I was trying to give you some wiring interpretation of it, right? Just like in the increment case, that was itself the enable, right? If you go back to the counter example, that is, whenever you say increment, there is no argument there. You're just saying do it, right? So that therefore there is a separate wire when you want to say execute this action method. Yes?
Could you explain the numeric type size?
Numeric type is always a number, and in this case, we can build a FIFO of any size, right? So it's if I write n there, that means the size. That means this FIFO is going to hold that many elements.
That's a number.
Right. Mm-hmm. Very good. Interface of a module defines its type, right? So this is just something you better get used to. Okay, now let's implement it. So this is my implementation of FIFO. We're going to keep our life very, very simple. We're going to implement a one element FIFO. And you'll be amazed how much mileage we're going to get out of one element FIFOs. They'll be used all the time in this course, right? One element FIFO, sometimes two element FIFO, right? So pay attention to one element FIFO. All right, so does everybody agree that it must contain the following methods in it? How do I know this? By looking at the interface definition, right? Interface definition says these are the 5 methods. I've just copied it. Okay, so now we have to implement it. So what about the state? It's a one element FIFO. So what kind of state do you want inside it? You'll have one register to hold the value, right? So you have a register, make me a register, right? And now this time I made make reg U. U stands for undefined. Its initial value is not known, right? So because we don't know the value of it, you can't use anything in this FIFO until you put it in. So initially it's undefined, and then I'm going to have one more bit which tells me, V bit, which tells me whether something is in this register or not. Whether it has a value or it doesn't have a value. So V is just a 1-bit value, which is either true or false. So far so good. Okay, so help me write these methods. So what is the not full method? Oh, sorry, this is, you have instantiated the state, right? Does this make sense? Right? Not V. It doesn't make sense?
Yeah, what's like make reg u? Is that like something you defined elsewhere? Like I don't get why one of them, like before, like make reg had a parameter that's 0. Right here, like make reg has a parameter that's false, and it seems like that's different types.
Right, so you can never figure out the type by looking at the right hand side. You have to look at the left hand side. What is the left hand side telling you? That you are making a register which is 1 bit and it holds values true and false. Correct? That false only tells me I have initialized it to false. In the first one, I'm making a register which holds things of type T. Okay? And I'm saying initially I don't know. So I'm giving you 2 different constructors. I'm making 2 different ways of making registers. Ones which have initial value, I call make reg, and I give an initial value. Or you can make a register whose initial value is not known. Then I just say make reg unknown. Make reg u. So these are primitives in the language. Okay, not empty. Well, if it has something in it, it's not empty, right? So V, just return V in this case. All right? NQ, what is NQ going to do? Remember, you can only NQ if it is not full. That was written in the previous slide. So if you do that, if you are using this object properly, then you would have checked that and you will say V gets true and D gets whatever value you gave me. And similarly, you can see DQ. All it's saying, there's nothing in it. So you just set V to false at that point. And first, just returns whatever is in register D, whatever is in the data registers. I claim this is pretty straightforward to write, right? If you understand the definitions, if you understand the representation, of it, that I'm using one data register and one valid register V, which tells me whether data register contains anything or not. All these codes are pretty straightforward to write. So this is the kind of thing you say, whoa, what is that? Proviso, bits T, something, right? You see, types can be anything in BlueSpec. But you can't store anything in a FIFO. What is the minimum property you want from the object you want to store?
I guess you're kind of allocating bits for T, like however big T is.
So what this says is that the type is bitifiable, right? It has some representation in bits. And the way you write it in BlueSpec is saying, the type T must be something that is represented in size T as Z. So this is another free variable. You don't know, how big it is. All you are saying is, please don't give me a T, right? Which I don't know how to represent in bits. You won't have to worry about all that because it will be done through pack, unpack, etc., right? The only assertion here is, if you're going to be storing some quantity, it must be bitifiable. It must have a bit representation in bits. Okay, so now let's use these FIFOs. Let's use it for streaming a function. If you're using it to stream a function, I'm writing something new here, but I'll explain in a second what a rule is. But under what condition this system will work? Under what condition f can be computed? F is some combination function. Only when there is some input, right? So input q cannot be empty at that point. And that's what you see here, in q not empty. Right? And since I'm picking something up computing F, putting it in the next one, that must have space in it. So that's what it's saying, output Q is not full. If that is the case, then what do I do? Who can read this? I'm reading the first element from the input Q, applying function F to it, and then I'm enqueuing it, right? That's what is shown here. And after I have done that, I'm done processing in Q, so I'm dequeuing it. So those are the two things that are shown here. This part is actually computing this value, right? On the first element, output Q is being output queued here, and after I have computed it, I'm dequeuing the input. Yep.
What does it mean to stream a function?
So the idea was that you have some combinational function F, and I want to repeatedly use it. Right? So I'm getting a whole bunch of messages which are coming through these FIFOs. So I take the first one, apply F to it, put it in the output queue. Take the next one, apply function F, put it in the output. That's what it means. Streaming a function, right? You're just repeatedly evaluating it. It's a very common paradigm. It happens a lot. Good. This is a Boolean AND operation. Now let me tell you something very interesting, and that will make our life easier. So we can make the life of the programmer easier, because what you saw in the case of FIFO happens in many, many module designs. You say, look man, don't do NQ unless there is space. Don't do DQ from a FIFO unless there is an element in it. Why don't we make them part of the definition so that you don't have to constantly test it? Right? I mean, that would be very convenient. So when we do that, it's called a guarded interface. And that's what guarded interface looks like. Every method has a guard. And you can think of a guard as a ready wire coming out. It's saying, yes, I'm ready. Right? I can be applied. If it's not ready, so now we are diverting from software. This is very hardware view of things. If ready is not true, you can't use that method at all. Okay. So now, a value method returned by a method is meaningful only if its guard is true. In other words, it's always returning something, but is it meaningful or not? You have to look at the ready wire. If the ready wire is true, that means whatever value you are getting is meaningful. Otherwise, it's not meaningful because it wasn't ready. So whenever you have a value coming out, there is an implicit ready line associated with it, and unless the ready wire is true, the value has no meaning. It's just, it could be whatever you want it to be. And for every action method, and this is the question that was asked earlier, has an enable signal, an enable wire, which is saying, please do it. I want you to do this, action method at this point. So this is the wiring diagram associated with this. And now when I write the interface, I don't have any more not full, not empty, because that's going to be all implicit in my definition. Because it's just more convenient to write it like this. So if you do it like this, then, and there is no mention of enable and ready because this is universal. We can look at the type and instantly tell, right? So this is what the definition will look like. This is without the guards. And now, this is the guard. Does this guard make sense? When should you do this NQ? When V is not full, right? And similarly, so there is no semicolon over there. And when can you do a DQ? When it has something in it, right? So that's the guard for it. When can you do a first? When it has something in it. So now what I have shown you is the same thing you wrote earlier, but now every method is qualified by a guard. under what condition this method can be used. And this is just, once you get used to it, this is like the best thing since sliced bread. Right? I mean, look at this. This code, you wrote it like this, but now you will write it, you don't have to write all that. You will just say, pick it up from here, put it over there. Why? Because there are implicit guards. You can't pick up something from the input queue unless it has something. You cannot put something in the output queue unless there is space in it. So this is being taken care of for you. Implicit guard methods are sufficient. Okay, so I have to stop here.